Hey there! Have you ever stopped to wonder how the internet really works when you type a website address into your browser? It's almost like magic. You type in www.example.com, hit enter, and boom, the page loads instantly. But behind that simple action, there's a lot happening. Quietly, invisibly, and very precisely. Today, we're going to break down 3 core technologies that make this everyday magic possible: NAT, DHCP, and DNS. These are foundational networking services, and once you understand them, the internet will never feel mysterious again. Welcome to BlueHat Cybersec Academy. Let's discuss in detail and unpack how these core networking protocols work, step by step, in a way that actually makes sense, even if you're just getting started. Let's begin with NAT, which stands for Network Address Translation. At its core, NAT acts like a translator between your private network and the public internet. Every device connected to the internet needs an IP address, which is like a digital home address. But here's the problem. IPv4, the most widely used version of IP addressing, only supports about 4 billion addresses. That might sound like a lot, until you consider phones, laptops, servers, smart TVs, cameras, and IoT devices, all competing for addresses worldwide. We ran out a long time ago. This is where NAT saves the day. NAT allows multiple devices inside a private network, like your phone, laptop, and smart TV, to share a single public IP address when accessing the internet. Think of it like an apartment building. Each apartment has its own room number, or private IP, but the whole building shares one street address, which is the public IP. NAT manages the traffic going in and out. Here's what actually happens behind the scenes. Your device has a private IP address that only works inside your local network. When you request a website, your router replaces that private IP with the network's public IP address before sending it out to the internet. When the response comes back, the router remembers which device made the request and forwards the data correctly. All of this happens in just milliseconds. There are several types of NAT, each used for different scenarios. Static NAT means one private IP permanently maps to one public IP. This is pretty common for servers that must always be reachable. Dynamic NAT, on the other hand, maps private IPs to public IPs from a pool, and these mappings can change as connections are made. PAT, or Port Address Translation, sometimes called NAT overload, is actually the most common type. Multiple devices share one public IP, and the router uses port numbers to keep all those connections organized. NAT is important for 2 big reasons. First, it conserves IPv4 addresses, allowing millions of devices to exist online using fewer public IPs. Second, it improves security by hiding internal IP addresses from the outside world. That said, NAT can sometimes cause issues for applications like VoIP or peer-to-peer services, which prefer direct connections. And with IPv6, NAT may eventually become less critical, but for now, it's everywhere. Now let's move on to DHCP, or Dynamic Host Configuration Protocol. DHCP is the reason you can connect to Wi-Fi without manually typing in network settings. Every time your phone, laptop, or tablet joins a network, it needs an IP address, a gateway, and DNS details. DHCP automatically provides all of that. No manual setup required. So, let's talk about how DHCP works, specifically the DORA process. DHCP actually follows a 4-step process known as DORA. First is Discover, where your device asks if a DHCP server is available. Next comes Offer, and that's when the server offers an IP address. Then there's Request, which is when your device accepts the offer. And finally, Acknowledge, where the server confirms and leases the IP. This whole exchange, by the way, happens almost instantly. Now, why is DHCP so important? Well, without DHCP, every device would need to be manually configured, which is just not practical in homes, and honestly, it's impossible in large organizations. Also, DHCP uses leases, so IP addresses are reused efficiently when devices disconnect. Of course, problems can still occur. For example, 2 devices might accidentally receive the same IP address, which causes a conflict. Or the DHCP server might actually run out of addresses, preventing new devices from connecting. Now let's talk about DNS, or Domain Name System. DNS is what allows you to type www.google.com instead of memorizing numeric IP addresses. When you enter a website address, your device asks a DNS resolver for the IP address. If it doesn't already know, the resolver queries a root server, a top-level domain server, and an authoritative DNS server. Once the IP address is found, it's sent back, and the website loads. DNS uses different record types for different purposes. A records are for IPv4 addresses, AADOA records are for IPv6 addresses, MX records handle email routing, and CNAME records are for domain aliases. DNS can be attacked through spoofing or cache poisoning, which basically means redirecting users to fake websites. DNSSEC helps prevent this by verifying the authenticity of DNS responses. Here's how everything connects. DHCP gives your device an IP address. NAT allows that device to communicate with the internet using a shared public IP. DNS translates domain names into IP addresses so your device knows where to go. Together, they form the backbone of modern networking. NAT, DHCP, and DNS may be invisible, but they're essential. They make networking scalable, secure, and user-friendly. Once you understand them, troubleshooting networks and understanding cybersecurity becomes far easier. Thanks for watching BlueHat Cybersec Academy. If this video added value to your day, give it a like, share it with someone who could benefit, and subscribe for more practical cybersecurity and networking content. Drop a comment below. I'd love to hear how you're applying these concepts in your labs or real-world networks.